Welcome back to NE 630 nuclear reactor analysis. So last time we solved the diffusion equation in a multiplying medium, and we showed that when you solve the time-dependent diffusion equation, the flux in a slab will be also time-dependent, but we solved the equation using the separation of variable, and this is a well-known technique for solving partial differential equations, which leads to a separation of the flux to two independent functions. One is a function of the position, or x, and the other one were a function of time only. And we combine both functions to form the flux. Then we looked at the solution in the position, and this leads us to defining the eigenvalues, or the eigenfunctions. In this case, the eigenfunctions were just a cosine shapes functions, and the eigenvalues were the Bn values that we got last time. So today we will continue the same business, but instead of solving this in a slab geometry, we'll solve it in a cylindrical geometry. I have also to remind you that the condition for criticality last time was K effective equal to 1, and we knew that K effective is nothing more than nu sigma fission over sigma absorption minus 1 divided by 1 plus L square V square, which is 1 over 1 plus L square V square was the non-leakage probability that we derived last time. And we stated clearly that the condition for criticality will be fulfilled when the geometrical buckling will be equal to the material buckling. And material buckling is just a factor that depends, or a parameter that depends only on the material properties of the critical system that you are talking about. So it just only depends on nu, sigma fission, sigma absorption, L square, and this is the material buckling. The geometrical buckling depends on the shape of the reactor. So in the slab geometry, we found that the geometrical buckling B1 square is just equal to pi multiplied by n divided by a extrapolated. So if you look at for slab geometry, the geometrical buckling was just n pi over a extrapolated, and this is for slab geometry. So now let's look at cylindrical geometry. So if we have a cylinder, finite cylinder with a radius r and height h. So this is the center of the cylinder, and we have r. Let's say we'll take r capital will be the extrapolated distance will be r capital. So this is the extrapolated distance, for example, and the extrapolated height will be somewhere less than this. So this is let's say h. Let's assume that the center here at 0 for the coordinate here in the center, and now we are interested in knowing what is the solution for this system. So again, extrapolated distance is just r tilde is the extrapolated distance, and this is just the radius of the cylinder plus 0.7 lambda transport, which is lambda extrapolated, and the height, extrapolated height, is also equal to h extrapolated, and this is just the height plus 0.7 lambda transport. Now the equation that we will solve is exactly the same reactor equation, nabla square phi plus b square g geometrical buckling phi equal to 0. So how to solve this in cylindrical geometry? Again, we will expand the nabla square, and it is 1 over r d by dr, r d phi by dr, and plus, of course, I have to do this as partial differentiation, because now I have a dependence on z also. So this is d by dz for phi plus p square g equal to 0. So this is a partial differential equation, in 2 dimensions, z and r, and I want to solve this equation. What are the boundary condition for solving this equation? Flux at the extrapolated distance at r and at any z. So the flux here at this border at any z, so at this z, this, at extrapolated distance r at any z equal to 0, and it is the same when you said that this is the flux at the extrapolated distance h at any r, giving any r. So when you are here at any r, this is equal to 0 also. But this is, we'll call it plus or minus h over 2, because h is the total height and the center is here. So we will make it h over 2, plus or minus h over 2. So now, to solve this equation, we have to do the same like before, as we talked before about the solving the diffusion equation in parallel pipe geometry, or solving the diffusion equation in another geometry. So what we do now is we will assume that the flux is just a function of r and z is separable. So it's a function of position r multiplied by another function, which is z capital, as a function of z small, which is the position here. So in this case, if you substitute with the flux like this in this equation, you will end up with 2 equations like before. And those 2 equations, I'm not going to go the substitution and everything, but if you will do this, you will notice that you will have 2 equations, one in r only, it's r capital with respect to r, and the other one is z capital with respect to z, and both of them equal to some constant, and this constant will be negative b square g. If you just divide those 2 equations by phi here and by phi here, and take phi from here and move it to the other way, this will give you negative b square. Then try to substitute phi here will be r and z, but z is constant because you are differentiating with respect to r, so z will come outside, but this is r and z, so z from up will go from z from down, and you will have 1 over r, and this function is r only. And here you will have 1 over z and d2 phi by d2 z by dz square, and this is a function of z only. And those 2 functions equal to negative b square. So each one of those functions should be a constant. Yes. So this constant, the first constant here, I will call it lambda square plus alpha square equal to b square g. Those are the 2 constants that, because if you will see here, you will notice that this is d2 phi by dz square. Yes, it will be transformed to d2 z capital by dz square. Yes. So if we write the z component, it will be d2z capital by dz small square 1 over z equal to negative b square, equal to alpha square, negative alpha square. What's this equation? d2z by dz square equal to negative alpha square z. We solved this equation several times. Second derivative of function equal to negative alpha square multiplied by same function. Yeah, this is the simple harmonic motion, and this is what we call the eigenvalue problem, which operator in this case is, what's the operator here? d2 by dz squared. And what's the function? Z equal to negative lambda square multiplied by the same function. In this case, lambda square is just alpha square. So operator, you are operating over a function, and you get the same function multiplied by a constant. So this is the eigenvalue problem. Yes? So what's the solution for this equation? Z capital of Z small is nothing more than some constant multiplied by cosine Z small plus another constant multiplied by sine Z small. But from symmetry, the flux has a cosine shape in the height, in the h direction. So from symmetry, I expect that the flux, because this is the center here, I expect the flux will be maximum in the center, 0 in the extrapolated distance. So cosine is the only function that will work for me. Sine will be like this. This is the sine. At 0 is 0, and at the extrapolated distances, one is equal to positive and the other one is equal to negative. Does it mean anything? Mathematically, no. There is no meaning for a negative flux. So the only function that will work for us will be what? Cosine. The cosine, and this is why I picked up the cosine. And again, you will solve this and you will substitute with the boundary condition. What is the boundary condition? Z at Z small equal to plus or minus h tilde over 2 equal to what? 0. Yes? And this will lead to what? This is, by the way, there is a B here. There is a BG here. And there is a BG here. Not a BG, it's a alpha, sorry, alpha. There is alpha. Alpha. So this will lead to what? Either A equal to 0, when Z equal to 0, either A equal to 0 or the cosine equal to what? 0. If the cosine equal to 0, this means that whatever inside is equal to what? N by over H extrapolated. Okay, guys? So in this case, I will reach from here, I will reach to alpha n is equal to what? N by over H tilde. What about the other equation? I will do the same for the other equation. So the other equation will be rewritten as the following. The other equation will be written as 1 over r d by dr, r dr capital by dr plus lambda square r capital equal to 0. Try just to rearrange this equation. If we multiply it here by r square and again here by r square, then this will be r square divided by r. This will be just 1r. Then this will be the first multiplied by the integration of the second, differentiation of the second, plus the second multiplied by the differentiation of the first. R with respect to r is 1 plus r square lambda square r of r equal to 0. So r by r is r square d2r by dr square plus r dr by dr plus r square lambda square multiplied by r equal to 0. What's this equation? We took it before in cylindrical geometry when we solve for the non-multiplying media inside a line source inside a non-multiplying medium. Do you remember? Bessel function, yes? But which one is Bessel function? To give you a note about Bessel function, just a hint about Bessel function. So Bessel functions. Bessel functions are functions in this form: x square d2y by dx square plus x dy by dx plus let's say, let's call this alpha square x square minus n square multiplied by y equal to 0. So this is the Bessel function, and the solution for this Bessel function will be what we call the Bessel function of the n order of alpha x, and this is the R2 functions, j and y. So you take whatever multiplied by x, take the square root of it, and make it the coefficient of x inside the argument for the Bessel function. So now, those are the two solutions for the Bessel function. If you have negative here, like when we solved last time for a line source inside a cylindrical medium, it was negative alpha square x square. So this will give me, if it is negative here, this is if it is positive, this sign here. If it is negative, this gives us last time, it gives us what? K, I and K. Give us in of alpha x and kn of alpha x. So this is called Bessel function, and this is called modified Bessel. So the modified, you will have negative here. So this is positive is the Bessel and negative is the modified, and we will have here. Now, if n equal to 0, I will get what? J0, and I will get the other one is what? Y0. And for this one, if it is n equal to 0 also, I got the modified Bessel functions of 0 order. Now, here for our case here, what's the n in this case? N is 0. So I will get of the Bessel function of the first, of the 0th order. But I will get the Bessel or the modified Bessel? Bessel function. So the solution will be R of R will be just two constants also, A prime multiplied by J of lambda R plus B prime multiplied by G naught Y naught of lambda R. So this is the solution. Now if I look at the solution and I plot the Bessel functions, I will notice that the Bessel functions, especially J naught and J1 and so on, I will notice that the Bessel function of the 0th order will be something like this, and this is J0, and J1 will be something like this. This is J1. If you look at Y is not symmetric at all. So which one is symmetric at the center? Because this also has a reflection here. So which one is symmetric at the center? G0. K is not symmetric. Y, sorry, is not symmetric. Y is not symmetric. So the solution, should I get a symmetric flux like this, because there is leakage from here, and the flux is maximum in the center, so I have to have symmetric flux. Yes? So the only term that I will leave here in those two terms will be what? J naught. Y naught will be equal what? I have to put B equal to 0. So I have to set constant B prime equal to 0 because of what? Because of symmetry of the problem. The reactor is symmetric. So y naught is not symmetric. Y naught is not symmetric at r equal to 0. At r equal to 0, y naught is not symmetric. So I have to eliminate y naught. How to eliminate it? I have to set up the constant equal to 0 so that once you multiply 0 by anything is 0. So in this case, your solution for the problem will be what? In the radial direction? Will be what? My solution in the radial direction will be just r of r, some constant a prime multiplied by g naught of lambda r. Now I can apply the boundary condition r at r equal to plus or minus, r equal to r capital tilde equal to what? 0. And if you apply this, you will notice that g naught at lambda multiplied by what? R tilde should be equal to what? 0. When or where g naught is equal to 0? It has several zeros. This is one of the zeros. This is the second. This is the third, and so on. It has lots of zeros. Yes? But last time, when we talk about the flux, and we said that all the higher harmonics will die out, and only I have to keep which one? The first one. So this is called the first one. First one. So in this case, lambda r will be equal to nu. By the way, nu is not the number of neutrons generated per fission. Nu is just, they sometimes call it nu, but nu is equal to 2.45. Okay? 2.45. So, of course, I can write this as lambda n equal to nu n, where nu n are positions of zeros of G naught. So nu n are, where are the position? Okay, guys? So nu 0 is the position of the first zero, which is at 2.45. Position of first zero. Okay, guys? So now, what will be the flux now for a reactor, cylindrical reactor? We will multiply the big function R by the big function Z, and in this case the flux of R and Z is nothing more than, it's a summation if you sum over all n, but again I told you that all n will decay except the first harmonic, so it will be some constant A multiplied by what? Cosine what? By Z over H tilde multiplied by what? G naught of 2.45 multiplied by R divided by R tilde. So this is the flux now. Now, what's B square J? Stated that B square J is equal to lambda square plus what? Alpha square. Yes? B square J equal to what? Lambda square plus alpha square. But what's alpha? So alpha square will be what? N by over h tilde square plus what's lambda? 2.45 r divided by r tilde square equal to b square g. So this is the buckling in cylindrical geometry. This is the buckling in cylindrical geometry. So if you are talking about a cylinder, finite cylinder, with height h tilde and with radius r tilde, the buckling, geometrical buckling, is equal to what? N by over what? Of course, if n equal to 1, as I picked up here, so this would be pi over h tilde plus 2.45 r over r tilde. When you equate this with the material buckling, this will give you what? Criticality condition. So critical when B material equal to what? Reactor is critical. Okay, guys? Again, how to get this constant A? Yes, go ahead.
I have a question with the little r.
Okay, little r.
Is it varying from 0 to big R?
Yeah, little r is any. If you want to get the flux at this position,
Okay.
let's say that there is a fuel here, a fuel rod here, and another fuel rod here, and another fuel rod here. So r will be the distance from the center to the point of interest.
Okay, but when you're calculating the geometric buckling,
Yeah, geometrical buckling will be not for the fuel, will be for the reactor shape.
okay, so
Because this is, you are talking about, I'm not talking about one fuel element, is it critical or not. I'm talking about my core is being critical or not based on the material inside the core and the shape of the core.
okay.
Yes.
I think the question is, do you have an R in your alpha is the term of R?
Oh, here you mean here?
Is that R?
Oh, sorry, I'm sorry. There is no R here. I'm sorry. There is no R. Thank you. It's my mistake. So the geometrical buckling is just the dimension for the reactor, the bigger dimension. Thank you. I'm sorry. Do you have any questions so far? So how to get the constant A? To get the constant A, we knew what's the power for the reactor. So the power of the reactor, how to calculate the power of the reactor, by the way? Okay, how many MeV are produced per fission? 200 MeV per fission. Yes? So if I multiply this is energy per fission, per single fission. If I multiply this by the total number of fission in the whole reactor per second, this will give me what? Power. Yes? Because energy per fission multiplied by fission per second, fission will cancel out and this will give me energy per second, which is power. How to do this is, this is epsilon F. This is the 200 MeV per fission. Now I have to multiply this by the number of fission in the whole reactor. How to get the number of fissions? Sigma fission multiplied by what? Flux multiplied by what? The volume of the reactor. Yes, guys? So this is total number of what? Fission. And this is the energy per fission. So this will give me what? Power. Now, the power of the reactor is just epsilon F multiplied by what's sigma F? What's sigma F is sigma F. What's the flux? I just show you the flux over there. So the flux is A multiplied by what? Cosine by Z over H tilde multiplied by what? G naught 2.45 R divided by R tilde multiplied by the volume. What's the volume if I have a cylindrical shell? What's the volume of a cylindrical shell? So this is R small, and this is delta R, and this is delta Z. So what's the volume? Cut this to a sheet. So the circumference will be what? 2 by R of this circle, yes? So when you cut this to sheet, you will have a sheet like this. The height of the sheet is what? dz. And this length, it was the circumference. So this is what? 2 by R. Yes? And this thickness was this thickness. It was what? dr. So it will be 2 by R multiplied by dr multiplied by dz will give you the volume. So I have to multiply it by 2 by R dr dz to get the volume of the cylindrical shell. Then I have to integrate from what to what? Z will be going from where to where? Minus h tilde over 2 to plus h tilde over 2. So this will be minus h tilde over 2 to plus h tilde over 2. And R, 0 to R tilde. Yes, guys? So if you do this and evaluate the integral, this will give you P equal to epsilon fission multiplied by sigma F multiplied by A multiplied by 4 multiplied by, you will notice that at the end you will obtain what? R tilde, and you will obtain what? H tilde. So pi R square tilde multiplied by H. This is what? The volume of the reactor. So when you do this, you will notice that you will get pi R square tilde multiplied by H. So this is the volume of the reactor multiplied by J1, because when you integrate this function, the J, the integration of J naught is J1. So you will note that you will get J1 of nu naught, and nu naught is what? 2.45. Okay? Over by nu naught. So now you can get, if you knew what's the power of the reactor, you can get the constant A. And the constant A will be just equal to 3.63 multiplied by the power of the reactor divided by epsilon F sigma fission of volume of the reactor. And that's it. So this is how to get the constant A. Because if you knew what's the power, you will put the power here. This is well known. Sigma F and epsilon are here. The volume is here. And then J1 at nu naught, you knew what J1 at nu naught. This is constant. Nu naught is 2.45. This is 4. This is pi. Do the multiplication, you will get 3.63 multiplied by the power divided by this. So this is how to get what? Huh? How to determine the constant A. So now, again, I show you the buckling for the cylindrical reactor. Again, we can solve the spherical reactor same way, and we will get the buckling for the spherical reactor. Okay, guys? We'll get the buckling for the spherical reactor. Now, there is something called optimum geometry. And what's the optimum geometry? We knew that our B square 1, which is B square J, is B square M, where I will have my criticality condition. Okay, guys?
B square is 1, you said?
B square 1 is B square J. J, B square J is the same as B square 1. Sometimes they call it 1, and sometimes they call it 1 because it is Bn, it was Bn, and n equal to 1.
This is the geometric buckling.
The geometrical buckling. Now, if you solve your diffusion equation in multiplying medium in the reactor shape of interest, so how many reactor shapes of interest do we have? What are the most common shapes of nuclear reactors?
Cylindrical,
Cylindrical, and what else?
spherical.
Yeah, spherical, and but the most common in research reactors usually, if it's not cylindrical, it will be barrel pipe. Like in our reactor in Egypt, we have rectangular mesh, where we have material testing, MTR, material testing reactor. It's a material, the fuel is blade type. So blade type, if you have a blade type, you cannot use a cylindrical. You have to use the fuel like plates, and then you put them inside barrel pipe, and then you put inside a cubical, or let's say rectangular shaped core. So now we have cylindrical, barrel piped, and spherical. There is hexagonal, MIT I think core. The research reactor has a hexagonal shape, but it's very rare. But there is hexagonal shapes. But the three shapes are those. So now we want to look for, I'm not going to derive it, it is in the book, but if we want to know what's the optimum shape, what's the optimum geometry, So for cube, for example, if you have a cube, you knew that what is the geometrical buckling? P square 1 for a cube. When we solved for a slab, it was what? Pi over what? Come on, guys. Last lecture. A extrapolated. So this is what? Pi over A square. Yes? So if I have a three-dimensional cube now, and the cube has A, B, C as dimension. So I can solve, and instead of this, it will be pi over what? Pi over B for the other dimension, and pi over C for the third dimension. Yes? And you will notice that you will have three equations, separable equation, one in X, one in Y, one in what? In Z. And the summation of the three equations equal to B square 1. So this will be equal to constant, okay? And this will be equal to constant, and this will be equal to a constant. Then when you get the first constant, second constant, third constant, the first constant will give you this, the second constant will give you pi over B, the third constant will give you what? Pi over C. So the buckling will be the summation of those three terms. So this is the buckling. Okay, guys? And then, in order to have a critical reactor, you have to have this buckling equal to what? The material buckling. Okay. Now, if I have a cube of dimension A, B, and C, and I asked you what is the optimum volume, for example. So you will notice that for a bare cube, the optimum volume is just equal to 161.11 divided by B cube M. This is bare cube, a cube, bare cube, and this is the minimum critical volume. So if I ask you what is the minimum volume for a cube, so you will tell me that the minimum critical volume will be 161.11 over B cube M. How did you get this? Again, from the criticality condition, and then you will differentiate. You'll say, okay, I need the volume to be minimum, for example. So you have to differentiate with in cylindrical geometry, or let's say take the simplest case. Simplest case will be what? Sphere, only one dimension, R. Yes? So if you want to get the volume minimum was one of the dimension like R, what you will do? You differentiate dV by d R and set it equal to what? 0. This will give you what is the R that gives you what? The volume minimum. But this is based on the fact that the geometrical buckling should equal to the material buckling. Because if I told you you have a sphere and what's the radius that make the volume 0, oh, minimum, sorry, will be R equal to 0. Yes? You will notice that R equal to 0 will make the volume 0. But this is not the case. I'm talking to you about the case that, okay, I need to have a material inside this volume, and the material buckling will equal to the geometrical buckling. And at this case, once the geometrical buckling equal to the material buckling, what is the minimum volume that I can have? So this is the minimum volume for a cube. For a cylinder, it will be V nearly equal to 1.4831 divided by B cube M. And for a sphere, will be equal to what? 129.88 divided by B cube M. Does the sphere make sense for you guys?
Yeah,
Why?
because they enclose the most volume with the least amount of surface area.
Yeah, so the sphere is the sphere, if I ask you from 101 geometry, what is the shape that has the minimum surface area with the same volume? So if the volume is the same but the surface area is the smallest, will be what? Sphere. So if I told you, I give you a material and I asked you the material is like, now we invent a new type of nuclear fuel and it is like clay. And I divide you to three parts. And I say, all of you guys will work in 3 groups, and I give you the new material now, which is clay, and you can shape it. And I will ask you, each one of your group will have equal mass, critical mass, which is BM, the material buckling. So equal mass, and I ask you, one of you will form a spherical reactor, the other one will form a cylindrical, the other one will form a barrel pipe. So I will not have, it's a uniform, I will not have fuel. Just you make your fuel as a solid cube, this is the reactor. I do not need to show anything inside. So if I ask you the 3 cases, so if the material buckling is the same in the 3 cases, BM, 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 and the 3 cases are the same, we notice that the optimum or minimum volume for the 3 cases will be what? The sphere. And why? Because the surface of the sphere is what? Small. And we knew from last time that if you want to get the leakage, it is the integration. The leakage is the integration of what? J dot dA. So whenever you have a smaller surface area, the total leakage will be what? Smaller. And because the sphere, if you have the same volume, let's say, the sphere, the volume of the surface area of the sphere is the smallest surface area, so it has the least what? Leakage. This is why you need a smaller volume if you have the same. So I will stop here, and next time we will start a new topic about reactor reflector. Now we solved the 3 cases or the 2 cases when we do not have anything but a bare reactor. So what if I put a reflector to enforce the neutrons that come out from the reactor to go back? Do I have a gain? Yes, we have gain. What gain is you can lower now your critical mass. You can say, okay, I will use a lower critical mass because I gain more neutrons. So this is called reflector saving. So next lecture we will look for what's the effect introduced by the reflector on those types of reactors and continue the rest of the course. Any questions so far? Okay, have a wonderful weekend.